A humanoid robot bends down, picks up a watering can, walks toward a shelf, and selects the exact object a person requested. Another robot seals a plastic bag, ties a trash bag, and unscrews a light bulb using 5 articulated fingers. None of these movements are individually impossible. The breakthrough is that one AI system is beginning to connect them into complete physical tasks. Google DeepMind has introduced Gemini Robotics 2, a new family of models designed to control robots from their feet to their fingertips. The previous generation could reason about physical environments and manipulate objects, but much of its humanoid work focused on the upper body. The new system adds walking, crouching, reaching, balancing, fine hand movements, long task sequences, and cooperation between different robots. Google is no longer trying to build only an intelligent chatbot. It is trying to build a general intelligence layer for machines that move through the real world. But the demonstrations reveal a central contradiction. The robots can now reason through surprisingly complicated tasks, yet many of their movements remain slower and more cautious than those of an ordinary person. The brain is improving rapidly. The body still has to survive reality. To understand why this matters, consider how traditional robots work. A factory robot is usually programmed for a narrow environment. A vehicle component arrives in a known position. The robot follows a predefined path, performs the same movement, and repeats it thousands of times. This approach can be fast and extremely reliable, but even a small change may cause trouble. Move the object, replace the container, or introduce an unfamiliar obstacle, and the robot may need new programming. A general-purpose robot must operate differently. It needs to see an unfamiliar environment, understand spoken instructions, identify relevant objects, decide what actions are necessary, and continuously adjust as the situation changes. That requires more than mechanical control. It requires a connection between language, vision, reasoning, and movement. Gemini Robotics 2 uses a class of system known as a vision-language action model. A language model predicts useful sequences of words. A vision-language action model must convert what it sees and hears into useful physical movements. Imagine telling a robot, put the groceries away but leave the fruit on the counter. The robot must identify which objects are groceries, distinguish fruit from other items, locate storage areas, decide how to grip objects of different shapes, avoid crushing delicate packaging, walk safely between locations, and know when the overall task is finished. A person handles these decisions almost automatically. For a robot, every stage is a separate technical problem. Google's approach divides the challenge into complementary layers. Gemini Robotics 2 handles direct physical control, translating instructions and visual information into movements. Gemini Robotics ER2 acts more like a supervisor. ER stands for embodied reasoning, meaning reasoning grounded in a physical body and environment. The supervisor can break a goal into steps, select the appropriate control tool, monitor progress, and respond when something goes wrong. This difference can be understood through a simple analogy. Gemini Robotics 2 is the skilled worker controlling the hands and body. Gemini Robotics ER2 is the manager watching the entire job, deciding what should happen next and checking whether each stage was actually completed. That final ability is more important than it sounds. One of the hardest problems in robotics is knowing when a task is truly finished. A robot may rotate a light bulb without tightening it completely. It may pull the sides of a bag together without forming a secure knot. It may begin pouring liquid correctly, but fail to stop at the right moment. Google says Gemini Robotics ER2 can continuously classify how far a task has progressed. Instead of seeing only started or finished, it estimates intermediate progress and uses that information to decide whether to continue, retry, or move to the next step. In Google's evaluations, the model achieved 57.4% accuracy when classifying task progress into 5 stages. That number is not close to perfect, but it represents the type of awareness robots need before they can work independently for long periods. The model also improved at identifying the exact moment when a critical event occurs. Google reports 91.3% accuracy on these moment-finding tests, with an average timing error of less than 1 second. That ability could tell a robot when a cup is full, when a screw is tight, or when an object has entered the correct position. The difference between a useful robot and a dangerous robot may eventually depend on 1 second. A machine that stops pouring slightly late creates a mess. A machine that stops applying force too late could damage equipment or injure someone. Intelligence in the physical world cannot be judged only by whether the final plan sounds correct. Timing, force, balance, and reaction speed are part of intelligence too. Gemini Robotics 2 also introduces more advanced whole-body control. Videos released by Google show Aptronic's Apollo 2 humanoid walking, bending, stretching, and manipulating objects while maintaining balance. This is a major change from controlling a robotic arm attached to a stable table. When a humanoid reaches downward, its center of gravity shifts. When it carries an object, the weight changes its balance. If it extends one arm, the legs and torso may need to compensate. A movement involving the hand is therefore also a movement involving the rest of the body. The robot cannot treat walking, reaching, and gripping as unrelated actions. It must coordinate them as one continuous system. Google has also demonstrated improved control of 5-fingered robotic hands. Hands are one of the most difficult parts of humanoid robotics because they contain many joints and must combine precision with force. Picking up a solid box is relatively simple. Tying a flexible trash bag is much harder. The bag changes shape during the task, parts of it can become hidden, and the robot must maintain tension while repositioning its fingers. Humans learn these actions through years of physical experience. Robots need demonstrations, simulation, sensor feedback, and large quantities of training data. This is one reason videos of impressive robot demos should be interpreted carefully. A successful demonstration proves that the task is possible under those conditions. It does not prove that the robot can repeat it thousands of times in every home or factory. Google acknowledges that movement speed still needs improvement. Real-world robots must also deal with poor lighting, reflective surfaces, damaged objects, crowded rooms, unpredictable people, and mechanical wear. A robot working in a laboratory may know exactly which cameras, sensors, and objects will be present. A robot working in a kitchen may encounter a wet floor, an open cabinet, a moving pet, and a child entering its path. The distance between a controlled demonstration and a dependable product is enormous. Safety therefore becomes the complication at the center of the story. A chatbot can produce a wrong answer without directly touching anything. A humanoid robot can move a heavy object near a person. The intelligence must understand both the requested task and the physical limits surrounding it. Google says its system includes human proximity detection and automatic safety stops. It has also introduced a benchmark called Asimov Agentic to evaluate whether physical AI agents behave safely across different scenarios. These protections are necessary, but benchmarks cannot reproduce every situation a robot may encounter. Safety will also depend on mechanical limits, emergency systems, independent sensors, workplace rules, and human supervision. The smartest model should never be the only thing preventing a machine from causing harm. Another important part of the announcement is multi-robot collaboration. Google demonstrated Gemini Robotics ER2 coordinating Aptronic's humanoid Apollo 2 with a separate Franka robotic system. This points toward a future where one general AI model does not belong to one type of robot. Different machines could share a common understanding of tasks and handwork from one machine to another. A wheeled robot might move supplies efficiently through a warehouse. A humanoid could climb steps or use tools designed for human hands. A stationary arm could perform precise assembly. Instead of building one robot that does everything, companies could combine specialized bodies using a shared intelligence layer. This is similar to how one operating system can support different computers and applications. Google may be attempting to build something like Android for robotics, a common intelligence platform that hardware manufacturers can adapt to many machines. That could become more valuable than selling a single humanoid robot. If Gemini becomes the software layer connecting robots from different manufacturers, Google could influence how physical AI systems understand instructions, access tools, and communicate with one another. However, Google is not alone. NVIDIA is building platforms for physical AI and robotic simulation. Tesla is developing Optimus, Figure, Aptronic, Agility Robotics, Boston Dynamics, and numerous Chinese companies are building humanoid and industrial machines. Japan is investing in national physical AI infrastructure, while factories around the world are searching for solutions to labor shortages and rising costs. The competitive advantage may not belong to the company with the most impressive demo. It may belong to the company that combines reliable hardware, affordable manufacturing, useful software, safety systems, and enough real-world data to improve continuously. Google has exceptional AI research, but it does not manufacture a mass-market humanoid robot. It depends on partners such as Aptronic, Boston Dynamics, and other hardware developers. That partnership model allows Gemini to work across multiple bodies, but it can also make integration more difficult. Every robot has different motors, sensors, dimensions, hands, and physical limits. Google has introduced an on-device version that can run locally and adapt to different robot designs. Local operation matters because a robot cannot always wait for a cloud server before reacting. Network delays or lost connections are unacceptable when a machine is balancing, walking, or operating near people. But the on-device model is currently available only to selected trusted testers. This is still an emerging platform, not software that anyone can freely install on a household robot tomorrow. Gemini Robotics 2 therefore should not be interpreted as the arrival of a robot capable of replacing any human worker. It represents something more specific and potentially more important. The software pieces needed for general-purpose robots are beginning to connect. Vision is connecting to language. Language is connecting to planning. Planning is connecting to hands, feet, and tools. Separate robots are beginning to share tasks. The remaining barriers are not small. Movement must become faster. Reliability must improve from impressive demonstrations to thousands of successful repetitions. Hardware must become cheaper. Safety must work outside laboratories. Companies must identify jobs where robots create more value than they cost. But the direction is now clear. The first generation of modern AI learned to communicate with humans through screens. The next generation is learning to understand rooms, objects, motion, and physical consequences. Google has given its robots a better brain, more capable hands, and the ability to coordinate entire bodies. The real test begins when those robots leave the laboratory and discover that the physical world never behaves exactly as planned.